In this video, we are going over the concepts of Chapter 4, which is titled Introduction to Organic Compounds. Let's first define what is an organic compound. An organic compound is made out of carbon. Carbon is going to be the essential element that we talk about in this chapter. When we look at carbon, you can see this cartoon representation that we have in the top right corner of the slide. There was a cartoonist that actually made superheroes for each of the elements in the periodic table, and this is the representation of carbon. Carbon can actually take the forms of charcoal, graphite, and diamond. That's why you see that the superhero actually has all those forms of carbon as part of its body. Now, when it comes to organic compounds, let's understand that carbon can be found attached to other nonmetals, including hydrogen, oxygen, sulfur, nitrogen, phosphorus, or at times halogens. Because organic compounds are made out of groups of nonmetals, these compounds are covalent. And since they are covalent, they will have covalent bonds. Compared to ionic compounds, organic compounds have low melting points and low boiling points. There's a large number of organic compounds that are not soluble in water. So what this means is that many of these organic compounds are nonpolar. Where can we find organic compounds? As you can see the images that is in the bottom right corner, organic compounds are present in very different materials. Plants, animals, medicines, clothes, shoes, gasoline, foods, they all have organic compounds in them because essentially, remember that organic compounds contain carbon. In this chapter, we are going to explore some of the different families of organic compounds that we have in this discipline. When we organize these organic compounds, understand that we organize them by what is called a functional group. And the functional groups are going to be specific characteristic attachments to carbon atoms. In this chapter, I actually classify these functional groups into large families, so it will be easier to go over them. Let's start talking about the family of organic functional groups that are known as hydrocarbons. Hydrocarbons are going to be organic molecules that are composed of carbon and hydrogen. There are 4 members to the hydrocarbon family. The first one that we observe here is called an alkane. And an alkane is when you have a specific organic compound that has carbon-carbon single bonds and carbon-hydrogen single bonds. Understand that alkanes are going to be the nature of organic compounds because the longest carbon chain that we're going to see is going to be a stretch of alkanes. Now, when we are identifying functional groups, understand that alkanes, since they are going to be stretches of carbons and hydrogens, typically we don't identify them in large molecules. The rest of the functional groups that I will be mentioning will be identifiable in large molecules. The next member of the hydrocarbon family is going to be a carbon-carbon double bond. You may observe that sometimes when it comes to organic compounds, we have an R. R stands for rest of molecule. And that may represent hydrogen or it may represent a carbon chain. In the case of the alkene, it's going to be an organic compound that has a carbon-carbon double bond. Next, we have alkynes. And an alkyne specifically is going to have one or more carbon-carbon triple bonds. Lastly, we have arenes. And an arene is going to have this hexagon structure that has alternating double bond, single bond, double bond, single bond, double bond, single bond. This specifically is known as a benzene ring. And because of the properties of arenes, understand that sometimes in some textbooks, you hear that they are aromatic compounds. Aromatic compounds are not necessarily mean that they have an aroma, because many molecules in chemistry have an aroma. Aromatic actually refers to the existence of a benzene ring in the structure. Let's now move on and look at the family of heteroatomics. Heteroatomic means that these functional groups are going to have atoms other than carbon and hydrogen. The first member of this family, as you can see, is alcohol. And in an alcohol, the R is representing a carbon chain. R cannot represent hydrogen because if the letter R represented hydrogen, that means that that will be water. So understand that the R represents a carbon chain. So if we have a carbon atom bonded to a hydroxy or hydroxyl group, that is considered an alcohol. Then we have an ether. When it comes to an ether, we're going to have an oxygen bonded to carbon chains on either side. So both R groups, in the case of the ether, represent carbon chains. Next, we have a haloalkane. And in the case of a haloalkane, understand that R is going to mean a carbon chain, and X is going to mean a halogen. Halogens are going to be elements that live in group 7A of the periodic table. Sometimes haloalkanes are also referred as alkyl halides because of the presence of that halogen in the structure. The next two members of the family of heteroatomics is going to be an amine. An amine is when R represents a carbon chain and a carbon atom is attached to a nitrogen atom. Now, that nitrogen atom, in the case of the example that we see, it is attached to two hydrogens, but that nitrogen atom could be attached to one carbon chain or it could be attached to two carbon chains additionally from the one that is present, at least the way that it is written, to the R group or the carbon chain that is to the left of the molecule. So when it comes to amines, it can have overall one carbon chain, two carbon chains on either side, or it could be surrounded by carbon atoms. The last member of the heteroatomics is a thiol group. And in a thiol group, similar to what we have observed so far, that R group is going to be representing a carbon chain. And that carbon chain is going to be attached to an SH group. So if I have my carbon atom attached to SH, that represents a thiol group. The next set of functional groups are known as a carbonyl because all of these functional groups have a carbonyl group. A carbonyl group specifically is when a carbon atom is double bonded to oxygen. So I'm going to take a moment and highlight the carbonyl group. And you can see that this is my drawing of a carbonyl group. And if we explore through the different functional groups, we have the presence of a carbonyl group on each of them. The first member of the carbonyl family, as you can see, is called an aldehyde. And in an aldehyde, your carbonyl group needs to be attached at least to one hydrogen atom. To the other side of the molecule, so the R group, it can be hydrogen or a carbon chain. It will still be considered an aldehyde. The next member that we have is a ketone. Ketones is when you have your carbonyl group attached to either side by carbon chains. So the R group here on both sides of the carbonyl are going to be carbon chains. So if I write the structure of a ketone, it's going to be C double bond O. On either side, I'm going to have carbon atoms with the attachments that those carbons will have. The next member in the carbonyl family is going to be a carboxylic acid. And when it comes to a carboxylic acid, your carbonyl must be bonded to an OH group to one side. The R group for a carboxylic acid can be hydrogen or a carbon chain. The next member of the carbonyl family is going to be an ester. And in an ester, we have our carbonyl group attached to a single bond oxygen, and that single bond oxygen is going to be attached to an R group. Specifically, the R group that we have next to the single bond oxygen must be a carbon chain. The R group that is on the other side of the molecule can be a hydrogen or a carbon chain. Lastly, amides are going to be the last member of the carbonyl family. In an amide, we're going to see a carbonyl group bonded to one side to a nitrogen atom. In this case, we have that nitrogen atom bonded to two hydrogens, but that nitrogen could be bonded to carbon chains. As long as we have a C double bond O bonded to nitrogen, that is considered an amide. So the R group here can be a hydrogen or a carbon chain. Where that these two hydrogens can be there or carbon chains can be attached to that nitrogen. Now let's explore by looking at some organic compounds how we can identify functional groups in them. So we have the following example. We have a selection of organic compounds, and by observing the molecule, we can actually determine what are the functional groups that are present. As an example, I'm going to do specifically acetaminophen. At this time, I'm going to write in the carbon atoms that are here, because one of the things that we're going to learn in future videos is how organic compounds are illustrated. This happens to be the skeletal structure of an organic compound, where we only see illustrated some carbon atoms, and others, which are bonded to hydrogen or other atoms, are there but are just implied. So if I write in the carbon atoms in this molecule, they will go as follows. There's a carbon atom right here. There's a carbon atom right here. Carbon atom right here with a hydrogen. Carbon atom right here with hydrogen. Carbon atom with hydrogen, carbon atom with a hydrogen. So now at least you can see illustrated the carbon atoms. When we are identifying the functional groups, I would like to highlight them so you can observe how we find the different functional groups in a molecule. Let's get started. Here we have a carbon atom bonded to an OH. And if you look at the list of functional groups, this specifically is called an alcohol. Here we have a hexagon with alternating double bonds and single bonds. That is known as an arene. More specifically, that is a benzene ring. In this molecule, we have a carbonyl group that is bonded to nitrogen on one side. We can see to the other side is actually bonded to carbon. And when we have a carbonyl group that is bonded to nitrogen on one side, that specifically is known as an amide. I'm going to write in the atoms here for the molecule vanillin. Vanillin is the molecule that is responsible for the smell and taste of vanilla. Take a moment and determine what are the functional groups found in vanillin. Make sure that you practice with the other molecules that we have on the slide. When it comes to organic compounds, let's understand that they are illustrated in different ways. So far in the semester, we have learned about molecular formulas. But the problem with molecular formulas is that they don't give us a lot of insight into the structure of a particular compound. At times, we can utilize computers in order for illustrating how the atoms in an organic compound are attached. And you can see here that in the ball and stick model, we can see the carbon atoms shown with this black dots. Hydrogen is illustrated by this white dots. And then we can see that because each carbon atom is tetrahedral, this is the conformation that in this particular organic molecule, which is an alkane, is going to adopt. The expanded formula, which is another illustration that we can utilize, it is the same thing as the Lewis structure for a molecule. When it comes overall in organic chemistry, we are mostly going to be utilizing the condensed structural formula and the skeletal formula for a compound. So, what is the condensed structural formula? In the condensed structural formula, you're just bringing in the hydrogen atoms that are actually attached to the carbon atoms in a molecule. So, for example, let's look at the example that we have here. In this molecule, if I carefully observe the different atoms, here I have a carbon atom with 1, 2, 3 hydrogens. That's why the first thing that we see in the condensed formula is a CH3. The next carbon atom is a carbon added to 2 hydrogens or contains 2 hydrogens. That's why we see a CH2. As we move along, we have another CH2. Next, we have another CH2. We have another CH2. And then we have a CH3. So as you can see, the condensed formula is just a Lewis structure in which you bring in the hydrogens that are attached to carbon. Now, let's understand that when it comes to a carbon atom, we always have only 4 attachments to it because carbon is one of those molecules that respects the octet rule. When it comes to the last illustration, which is the skeletal formula is actually showing the different angles that each of the tetrahedral carbons will adopt. So when we're drawing the skeletal formula, let's understand that the minute that your writing utensil touches the surface of where you're writing, that's going to be carbon 1. And then you're going to move and draw on a line, and at the end of that line, there's another carbon, so that's carbon 2. Down, carbon 3, up, carbon 4, down, carbon 5, up, carbon 6. And here we have the illustration of the 6 carbons in this molecule. Now, the reason why we actually do it in the way that we create hills and valleys is essentially because if we relate it to the ball and stick model, the skeletal structure is actually illustrating the 109-degree angles that are going to be existing between the atoms for a tetrahedral molecule. So that's why we illustrate the skeletal structure in this manner. For the purposes of this course, it is okay with me if you actually write those dots in order to illustrate the existence of the carbon atoms. The only thing that you cannot do is actually write in the carbons and hydrogens in a skeletal structure.